All right, welcome back, everybody. So again, last week we talked about one way to actually find the electric potential. The way that we talked about was we can add up the electric potential due to a whole bunch of charges in our system. And those could be discrete charges where I've got 1, 2, 3, or it could be a continuous distribution of charges where I've got a line of charge or a sheet of charge or anything like that. But that's not the only way that I can figure out what the electric potential is. In fact, we did a lot of work over the first few weeks to figure out what the electric field from various charge distributions is. And if we already know what the electric field looks like, then we can actually integrate the electric field to get to the electric potential. I'm going to show you why we can do that down here in my equation. You'll see that we can kind of go back to our basic 211 knowledge, where we defined the change in potential energy to be the negative work done by the force. Actually, there's a restriction on this. This force has to be a conservative force for us to be able to do this, but good news, the electric force is a conservative one, which means we're allowed to make this definition. And then we know how to calculate work. We did that a little bit last week. We did it a lot way back in Physics 211. We simply have to take the force, multiply it by the distance that we're moving, and add all of those pieces up with an integral. And again, this little negative sign comes along for the ride in our definition of the change in potential energy. The way we can get to electric potential from this is simply to divide by one of the Q's that shows up in the electric potential energy. And you can see I've done that down here in the bottom line. And when you do that, you divide delta U by the Q, and that gives you delta V. That Q is a constant, so it easily goes inside of that integral. And then F over Q, we can kind of harken back to our definition of the electric force, is just the electric field. And so now we suddenly have a relationship between delta V, the change in electric potential or the electric potential difference, and the electric field. And that relationship is an integral one. We can integrate the electric field, and that'll give us delta V. Now, I mentioned that the electric force is this special conservative electric force. And that's simply fancy math language for saying that it doesn't matter which path we choose to take our integral, which basically for us means we can pick the easiest path in the world for calculating our delta V. Don't kind of go in weird squiggly lines. You want to take either a straight line path or maybe a path that follows the electric field so that that dot product is always a friendly one. I'm going to show you one example of what we can do with this. It'll kind of verify one of the expressions that we've already got. So here are the three really common electric fields that we found, gosh, a couple weeks ago now. The top one here is the electric field from a point charge or sphere of charge. The second one was the electric field from an infinite line or a cylinder of charge. And then that third one is the electric field due to a sheet of charge. We're going to talk about all three of these at different places. Today, I'm going to talk about the point, kind of the easy one, just to get our feet wet here. You'll actually talk about the line one a little bit on your homework, and we'll do the sheet in class on Tuesday. So I want to talk about the point charge here. So I'm going to draw a quick little picture. And my picture is going to be, here is my point charge. And I know what the electric field looks like, and I'm just going to live for the moment in kind of one dimension, right? So there's a big electric field here, and that electric field gets smaller, then it gets really small out here. And of course, it wraps around, right? The electric field keeps doing that everywhere in space, but I'm going to just draw this kind of one-dimensional picture here. And if I want to know what the electric potential difference for this system is, basically I just have to pick let's switch colors here. I just have to pick a couple of points. Let's pick this one and one way out here. And then I integrate from one point to the next. So I'm going to go ahead and start here. So I'll put a little I, that's my initial point. And then over here is my final point. And I'm going to travel from this dot to that dot. Now, again, I can pick any path to go from that point to that point, but you can see that like a squiggly one like this one, not a good path to choose because the electric field changes. It doesn't point parallel to the path. That's kind of a bad path to choose. I'm going to choose the straight line path. I'm going to go straight in from this point to that point. And I'm going to do this integral, which I realize is not on our screen right now. I'll maybe quickly pop back over here to show you, right? I'm going to integrate from Ri to Rf, the electric field dotted with dr. So I'm going to very quickly kind of note the path here. So we're going along dr. If I'm going from the initial to the final point, this is actually going to be dr kind of magnitude and then minus r hat, right? Because I'm going back. I'm getting closer to the point charge. The electric field, of course, I know is K times the magnitude of the point charge divided by r squared in the r hat direction. And then I have to take this integral. So I want delta V to be equal to the negative integral from Ri to Rf. And then you do this dot product between the electric field and the dr vector. And I specifically chose my path, so that would be an easy dot product, right? R hat is 1. Those two vectors have length 1 point in the same direction. There's a floating minus sign in there that comes along for the ride. You can conceptually think of that as the electric field, in our case, points to the right, but our path points to the left. We get a negative sign that kind of comes along for the right here. So we get minus K, not dq, q, dr over r squared. And you can see that these negative signs now are going to cancel out, right? -1 times -1 is 1. Some of these things are constants, k and dq. Those are going to pull out of our integral. And then the integral of r squared dr, or sorry, 1 over r squared dr is minus 1 over r. So another minus sign is showing up here. A lot of minus signs in this problem. So we're going to get minus kq divided by r, and then evaluated from ri to rf. And hopefully you're kind of looking at this expression and going, wait, I already knew what the electric potential was, right? KQ over R is what the electric potential for point charge is. Of course I should get this answer.